0.3.
All right, so we're going to do number 5 here. We've got a point charge that happens to have the negative type of charge on it at the origin. And then it says where must an electron, what type of charge does an electron carry? Negative type. Acting on it, it'd be exactly opposite its weight. Which direction does the weight of something act? Down. So what would be exactly opposite of down? Up. Oh, okay. So we want the force on this electron caused by this other negative charge to be upwards. Right? All right, so I did a force diagram for it. I think you should too. So I'm going to put my other negative charge right here at the origin. Call that negative. And so they are telling us that up we have to call positive. So, whoops, I meant to put that more in the middle of the screen. So if I want the electrostatic force on the electron to be upwards, where compared to this charge should I put the electron? Above it, right? Because they're going to be repulsed, which means, yeah, okay. So I should put the electron like here. And that's our electron. So it's going to have a force electric that's repulsive, just like this one will, right? Why can I label those the exact same? Because they're part of a force pair. And then the electron also has its weight acting downwards. And that's my whole force diagram. Well, I think that's why, for me at least, when it goes through my hand, it makes more sense. So that's why I always try to do these myself as someone else is doing it. That's what I found worked for me. Yeah.
For that clarification, the force compared to the force of gravity on the electron
would be down on the Earth, coming upwards. Yeah. But since the Earth isn't in my diagram, I didn't draw that force there. Hey, what's up? Not unless, if it was a task or something that said draw all the force pairs, then I would. But no, really, I don't even have to have that other electrostatic force on the red charge, because I'm only interested in the electron. But I figured I'd add it in there to reinforce that force pair thing. Hi, Sarah. All right, so I think if you look at the rubric, I hit all the points. I showed the situation. I did all the force diagrams required because I'm only interested in the electron, so I did one of the electron. Force is shown and correct. Yay. Labels on the diagram were easy to understand? I think so. Acceleration shown and correct. Did I show acceleration? What is acceleration? I don't even know, so I shouldn't even have to worry about that part. Yes. Free 20%. Nice, yeah. We haven't learned about it, so I'm not going to count it against you.
So I can get a minimal of 20% minimum.
Yep, even if you at this point, even if you screwed up everything on your force diagram, you still get 20%.
That's awesome.
Yeah. That is. All right, so now I need to start with valid physics equations. From I know it told me that it's an equilibrium, so the total force, that's right, we got to have that Greek quiz. Okay. I know when we'll do it. And then I should probably, from my equation sheet, grab Coulomb's law and probably grab the equation for weight. All right? Minor, but becomes a point that becomes a stumbling block for some people. Notice on Coulomb's law, is that a vector or a magnitude? Right, it's a magnitude because it doesn't have the little half arrows above it, which indicate vector. Remember, that's Coulomb's law. That's the weight of something. In fact, I left off my little g, sorry, my big G, sorry. When we use Coulomb's law, it's to figure out the magnitude of the electrostatic force, not the direction. We already did that because we know that these two are repulsive. So we already know it goes up and down. This is to figure out how big the force is, not the direction of it. So never should have, it's only magnitude, it's only value, not positive, negative, because that has different meaning. I can't hear you. That means that they told me that the electron isn't moving, is in equilibrium. So that means the total or the net force on it is 0. So back to Coulomb's law here. One of the biggest mistakes, and someone will do it, or already has done it in this room, will be when you're putting the charges in, you'll put the type of charge also. That does not go in here. It's just how big the things are, not the type. You don't care if it's red or blue, right? Okay? So be cautious of that. All right, so let's see. How many forces did we have on the electron? Two. We had one upwards and one downward. Which one was going up? Oh, that was the electrostatic force, right? So this needs to be vectors, so I'm positive plus a negative weight, because it was pointing downwards. So now I've got the magnitudes of them, but I've taken into account the direction, right? With making the upwards one positive, the downwards pointing one negative. That's taken into account the direction. That's why that first F was a vector. The direction matters when you're adding them together. Now I can just work with magnitudes, how big things are. Oh, look, those two have to be equal. That's cute. Now we can substitute in, right? K, Q1, Q2, R squared equals mg. I don't know, it made me happy. I don't like negatives, because what happens is I do a math step and I forget to write the negative. So if at all possible, I get things out of negative. So I was just doing that because I know one of my tendencies is to leave off negatives, and it screws me up.
What does the mg represent again?
From our equation sheet, it says the gravitational force on something, commonly called the weight, is its mass times the gravitational field strength.
So why is that?
Well, because we were told that the electron's in equilibrium, which means all the forces add up to 0. There's only two forces, one pointing upwards, the electrostatic force, and one pointing downwards, the gravitational force, or the weight of the electron. And those two have to add up to be 0. So I just followed my math. I did skip a step in there, but I followed my math and they came up to be equal. You want me to do that step I skipped? Okay. But that's why.
I don't understand why you said
I didn't.
Okay.
Equals. Now, all of you agreed with that drawing. How many forces are on the blue electron? 2. So representing that drawing mathematically is right here. Here is that drawing written in the language of math. They're the same exact thing. One's written in the language of visualization, and one's written in the language of math. But that's where I got that from.
Because you don't need to use the vector on the weight of the second one because it's not triangle. It's not trying to line. Like when next to like on the bottom of the negative times 1 2 divided by r squared equals mg, but you don't use vector there because you're not like.
Well, nice when I put things into math here with the circled one, I took into account the vector nature. So let's back up one step, okay? So I think this skipping steps is harsh on some of you. So here's the intermediate step here. The intermediate step says, okay, take the vector that is the electrostatic force and add it to the vector that is the gravitational force, and those are going to add up to 0. And then the vector that is the electrostatic force is positive either. The positive is the direction, the F sub E is the magnitude. Oh, here, here's that magnitude thing again. Right? And then this one, that vector is here what's in parentheses. The direction, the negative, and the magnitude F sub G. Now that I've put those vectors in, I can now, and I've represented their directions by positive and negative, I can do what you guys would think of as traditional algebra on them. Okay? And the step that I skipped in here, mathematically, was I could have written Fe minus F sub G equals 0. I skipped that math step. But you're right, I skipped some math steps in there. But it makes, I'm glad you asked, because if it makes sense now, that's better. Good. Okay. We ready to go forward? Forward.
Wait, I have a question.
Yep.
Well, just a concept of mine. Like, it gives me 1, 2, so like, I still understand the Q2 part. Like, if it gives you 1 and 2, where's the Q1 and Q2? But where's like the second?
So what two charges are interacting in this problem? So let's go back to the problem. Do we have two charges that are interacting?
Yeah.
Which, just give them names. Which one is which?
Positive.
They tell us one's at the origin, right?
Oh, yes.
Okay, so let's call that origin charge. Origin charge. What is origin charge interacting with? The electron. Oh, that's the other charge thing. So one, either Q1 or Q2, it doesn't matter which one, will be how much ever charge origin charge has. And the other one will be however much charge the electron has.
Oh, okay.
Those are the two things interacting. So remember, all forces are interactions between bodies. So in this case, to have an electrostatic force, you have to have two charges interacting. So those are our two charges. All right.
So if it gives you a 2 in this problem, then you take the other one with the electron, and that's like the Q2 of it? The problem?
Sure. Sure. Yeah. In this case.
Okay.
Wait, can you explain that?
Okay. Explain what?
What Virginia just said. So
Virginia was questioning which two charges were interacting to create the electrostatic force. And so we looked at the problem, and they told us that there was a charge at the origin. So we called that the origini, or the origini charge. And then we said, what was the other charge that one was interacting with? And we realized it was the electron, because the electron is a charge. So the two charges that are interacting are the origini one and the electron.
okay.
That was our whole discussion. Okay, that would probably be our next step. So I guess at some point we should probably look at the problem and say, what are they asking us to find? What distance? The distance between the two. They're asking how far apart should these two charged objects be. So that would be how far apart they are, r. Yes. R doesn't necessarily stand for radius. R stands for from one point to another. Math teachers probably haven't told you that because they don't think you can handle that fact. Or they don't know that fact. One of the two. Yes. But remember, R means from one point to another. It doesn't mean from the center of the circle to the outer part of the circle. Oh, but that's one point to another. That's why they use R for that. Cool. Well, if you consider physics is understanding and the math is really used just to kind of express that understanding, physics came first. Although it could be a chicken-egg type thing. When you think about calculus, why did Newton invent his form of calculus? Because it was an easier way to express his ideas in physics. All right. So, let's see. Let's see what are these mathy variables that we know. Do we know what universe this takes place in?
No.
Maybe. Well,
Our universe.
the only universe,
Oh.
by definition, right? Universe. So we know K. Oh, we figured out what the two charges were, right?
No.
That's what you and I were talking about.
Kind of.
Kind
Not
of.
really.
We want to know the distance between them. That's R. Do we know the mass of the electron?
Yeah.
Yep. Okay. And do we know what planet this takes place on?
Earth.
Earth. So we know the gravitational field strength. Because
Actually,
that's on our equation sheet.
that's a word.
How do we know it takes place on Earth?
Oh. Is that what G stands for in this?
Yep, little g. And I think that's on the most helpful sheet in the world, our equation sheet. It probably is. Oh, look, there's the mass of an electron. There's the gravitational field strength.
They also have G.
Yeah, it was nice of them. They don't know you have the most helpful sheet in the world.
They don't know
They don't know that.
What's R squared? Oh, wait, yeah. Oh, no.
In brain part.
Wait, so what's the equation of R squared?
Well, it's all math people really like it if when we set up an equation, we have one thing to solve for.
Oh, what's R squared?
That's our one thing to solve for.
What's MG?
Well, what object are we talking about?
The electron.
So if M would be the mass of that object, which in this case is an electron, the mass of an electron. G is the gravitational field strength of whatever planet this takes place on, and Hayden said it takes place on Earth. So that would be from the most helpful sheet in the world, 9.81 newtons per kilogram.
So the
So it looks like we know everything in these math sentences except.
Oh, right. Sorry, I knew that.
Okay. Looks like we know everything but R.
Yeah, students solve that.
That is the mass of the object that you're looking at, in this case an electron.
Oh, I have that. I have that.
So the question is now, it's up to you which way you go, right? Some people would substitute in and solve for R. Some people would solve for R and then substitute in.
And then what are the
Yeah, 1 newtons per kilogram.
9.8 like
Newtons per kilogram.
isn't it times something?
No.
Oh, sorry, found it.
I think I'm going to substitute in. There's some very common mistakes here, folks. Some of them come if you don't know how to use the exponent key on your calculator. That's a very easy common mistake. I guess I'll use green. So I'm going to substitute in. K I know is 8.99 times 10 to the 9th Newton meter squared per coulomb squared. My Q1, it tells me my Q, I'm going to call the originating one to be this Q. They tell me it has 0.45 nanocoulombs of charge. The little N in front of the coulomb. So I better look at the best sheet in the world, nano. 10 to the minus 9. So I better make sure that I put in my 0.45 times 10 to the minus 9, and so I get coulombs. Because my constant is in coulombs. So unless I want to do a lot of converting afterwards, it'd be nice to have my charges in coulombs. Let me finish this one last thing. And then, of course, I put in my 1.602 times 10 to the minus 19th coulombs for the charge on my electron.
Where did the 1.6 come from?
The world's greatest sheet, right here,
So that's playing
tells me that one quantum of charge, which is how much I know an electron carries, is 1.602 times 10 to the minus 19th coulombs. Man, what would I do without the sheet?
even with or without the sheet on the wall.
So, someone said they had a question, and then
So,
is that you? Yeah. Okay.
Shouldn't the Q1 be negative because it is in the problem, but you wrote it as positive?
Now, earlier in the problem, we did a public service message about Coulomb's law, and we noticed that none of it is vectors, that all of it is just magnitudes. So, to find out how much magnitude of the electrostatic force there is, I use the magnitude of K, the magnitude of each of the charges, and the magnitude of the distance between them, without worrying about what type it is or the direction of it. And the main reason we do that is in most of our mathematical calculations, positive and negative indicate direction. Is that true of charges? No, positive and negative indicate type of charge. So to clear up the confusion between what positive and negative mean, we just deal with the magnitude for Coulomb's law. I find it sometimes better to think of charges not as positive and negative, but it's like George and Albert. So I think I forget about the positive and negative, which can screw me up. Does that help?
Yes, sorry.
No, but I'm glad you said that, because I guarantee you there are three people that put in negative and said, "Oh, he must have just forgotten that," but I didn't.
Oh, wait, that answered my question.
Excellent.
This is a really question. But
That's okay.
why?
Okay.
I know little g is 9.81 times. Just 9.81.
Yes.
Why are we using that instead of 6.67%?
because the weight of something. Okay, good question. I'll do it as a sideline over here. Okay? So we know that the gravitational attraction between two objects can be described by Newton's law of gravitation, which is F big G equals big G M1 M2 over R squared. Right? We also know that the gravitational field strength around a planet is little g equals big G mass of the planet over radius of the planet squared. So if I'm on the surface of a planet, how far am I away from its center? Its radius. So I'm going to look at the gravitational force on me on the planet, otherwise known as my weight, right? So the gravitational force on me is going to be big G, whatever my mass is, mass of me, over the mass of the planet. Let's keep it generic. Maybe I'm standing on Neptune instead. Over how far I am from the center of the planet, which, you're right, just is the radius of the planet, and I square that. Okay? I should have used a couple different colors here, but I didn't. I'm going to now see, can I substitute this into here? And I can, because this and this and this are all contained in my other circle. So I think I need to do one more algebraic step so I don't lose people. I'm going to rearrange this bottom equation to be f sub g equals, I can pull my mass out front, right? And then have a big bracket here, and this be g mp over rp squared. Right? But that is that. This in the square bracket is the gravitational field strength. So I can maybe do a little shortcut because I use this so often and say my gravitational force, otherwise known as my weight, is my mass times the gravitational field strength on the planet. So that's where it comes from. And that's why it's little g, because that's the gravitational field strength, not the universal gravitational constant, which is big G. You got it. Okay. Oh, I was in the middle of substituting, wasn't I?
Yeah.
Okay, make the math people happy. Give them a variable. There we go. And then the mass of an electron. Ooh, all of this needs to move. I'm running out of room. Get over there. Stay. The mass of the electron. 9.11 times 10 to the minus 31 kilograms. And then, sorry, I'm going to have to go up the board here. My little g, because I'm on the Earth, is 9.81 newtons per kilogram. Find R.
Got it, ticket, got it right.
We do have an exit ticket, so
Yep, I think
if you guys can do that exit ticket,
Oh.
that would be great.